For module number 31, I'm just going to explain what's on page 48. So hopefully you had a chance to read it over. From the previous part, you were looking at the relationship between Kas and Kbs because they can be calculated and there's an inverse relationship there. The stronger an acid is, it's got a weaker conjugate base. The stronger the base, the weaker the conjugate acid. Okay? Now let's have a look specifically at the acid-base properties that the salt that you get when you have a neutralization reaction, how does that affect the pH at which the neutralization will be found? Okay, we're going to look at the salt and then we're going to see if it came from a strong or weak acid or base. What kind of conjugate does it produce? Because there's an inverse relationship. And then if it produces a conjugate that's strong, it's actually going to act like that acid or base and have the strength to pull water apart. And that's going to translate into the next module where we look at, do you have excess ions in that solution? And if the excess ions happen to be the hydrogen ions, that when a neutralization reaction takes place, it might not be at a pH of 7 because of the fact that you have a salt in the solution that can act like an acid or a base and pull apart the water that's also there. Okay, so a little bit tricky, but bear with me. You're going to read through this page a couple of times. Here's the short explanation of what's happening. Okay, ions that come from a salt can react with water. They can pull the water molecule apart and produce these hydrogens or hydroxides if they're strong enough, if they have enough pull for those hydrogens. The extent to which the hydrolysis occurs depends on the conjugate of that ion. Okay, the extent of the reaction can be quantified because Kw equals Ka times Kb. Inverse relationship. So let's look at these three different scenarios that we've got. Scenario number 1, you have sodium chloride. So let's say you had hydrochloric acid, sodium hydroxide. The salt that you make came from the sodium ions in the sodium hydroxide, and the chloride ions came from the hydrochloric acid. You recognize these as both strong bases and strong acids. Okay, so can you see that you got this ion from a strong base? That ion will then produce a weak conjugate acid. And it's weak, it's not strong enough to pull any water apart, and so you don't get any hydrolysis of the water from the sodium ion. Let's look at the chloride ion. Came from a strong acid. So it's the conjugate ion from the hydrochloric acid. Strong acid produces what kind of conjugate? Weak. So weak that it cannot break apart water. And so when you get a reaction, a neutralization reaction where you have a strong base and a strong acid reacting, they produce weak conjugates of the salt. They cannot pull water apart. And so when you reach an equilibrium, when you reach the neutralization point of these reactants, you will end up with a pH of 7 at that neutralization point. Okay? Why? Because the hydrolysis does not occur, the equilibrium is not shifted any which way, and therefore the pH of the sodium chloride in that solution is going to be 7. Let's look at the next two examples. So we're going to have an example where we have a weak base and a strong acid. Then our last example is a strong base and a weak acid, and that leads us into looking at titration curves for our very last lesson. Okay, so let's look at this, see if you can follow along. Potassium fluoride is a strong electrolyte. Why? Because it came from the potassium ion, came from potassium hydroxide, strong base. A strong base produces a weak conjugate. No hydrolysis will occur because of the potassium. But that potassium hydroxide was reacting with a weak acid. Okay? The fluoride ion came from that weak acid. A weak acid produces a very strong conjugate base. It acts like a base. It's going to be a proton acceptor, and look what's happening. It'll pull water apart attached to the fluorine, and now you've got hydroxides. So then you had some hydrolysis of water, and what kind of ion is left in that solution? Hydroxides. So because it occurs, you have an excess of hydroxide ions. When that neutralization reaction occurs between a strong base and a weak acid, the pH will actually be in the basic range because of the excess hydroxide ions that are there. Okay, you still have reached the neutralization point, but it just means that you better choose an indicator that's going to change color when you know it's going to happen because of the effect of these conjugate salts that happen to be in the solution, and they can affect the water molecules that are there. Because remember, acid plus a base gives a salt plus water. Now, what happens to the salt? Can it act like a strong or weak acid or base? Sometimes they can. Okay, so then the third example, did I skip over the second one? Oh, I've only got 2 examples on this page. I used to have 3. All right, you can see that the third example would be, oh no, there it is. I just didn't explain this one. Aluminum chloride, or ammonium chloride. Let's do this one quick. Weak base, strong acid. Okay, those are the 2 you start with. We know that the weak base produces what kind of conjugate? Strong. Strong acid, proton donor. Look what's going to happen. You're going to end up with hydrogen ions in that solution. On the other hand, you had a strong acid, which produces what kind of conjugate? A weak base. So weak that this cannot happen. So when you've got a situation where you have a weak base reacting with a strong acid, they produce a salt that has a strong conjugate acid of that NH4 plus, so strong it can act like a proton donor and donate its hydrogen ions, and then at that neutralization point you have an excess of hydrogen ions. So even though you've got a neutralized solution, your pH at which point that becomes neutral is in the acidic range because of those excess hydrogen ions that you've got. Okay, so that's the trickiest part with this. Make sure you go over this just a couple of times because we're going to take this information and look at it on Friday as part of the titration curve, and we're going to see at which point on the curve can you pick out the actual neutralization point or the equivalence point. Okay, that's it for today. Thanks, guys. We'll see you next time for our very last one.